Good morning, everyone, or whatever time it is by the time you watch this video, or by the time my assistant uploads this video at some point. We're going to talk about, in this particular video, we're continuing with the series on logic that I told you about. By the way, thank you all who have, it has been an immensely popular video, and I didn't expect it to be as popular as it was, but I'm glad that, I'm driving the message home. You need mathematical logic. I was tempted recently. I'm probably going to actually do it. I'm going to create a T-shirt for young people on their not when they're in class. No T-shirts in class, by the way, but I mean in their spare time. Perhaps they can wear it and commit it to memory. Math, not meth. Math, not meth. We need more math in this country and less drugs, and no drugs at all, really. But this video is going to be talking about quantifiers. So the first part, we're going to remember that I'm going to link in the description the previous video so that you have a content. Remember that I told you that you had to know what the symbols were before these videos even make sense. So there will be, so make sure you know those symbols, but we're going to talk about how they are used as quantifiers, the quantifier symbols, and then we shall discuss techniques of proof. As a first part, there's really two parts to the techniques of proof, but first I'm going to show you how to use quantifiers in this video, and then some mathematical techniques of proof, since a lot of you have asked me about that. It's extremely important, and a lot of schools don't ask students to prove anything. They're more concerned with certain vocabulary than they are with actual mathematical logic, and you know exactly what I'm talking about. So we're going to discuss those. The techniques of proof, and I'll show you some examples, and hopefully as usual that we have a productive session. And if you are interested, here's a message to someone wrote to me the other day in the comments. They said that they wanted to ask me a lot about my theological beliefs and all of that. I don't think a comment section is an appropriate place to do that, let alone an email, right? When you have very deep questions like that, which I welcome, by the way, that's why you have to write to me. I only answer very long things if someone actually takes the time to write to me, because then I know they're serious. Why would I spend time answering some emails sitting in front of a screen if I either don't have any guarantee of a response, or the person just doesn't agree with me for whatever reason and has no argument? And also because emails are mostly, our city tutoring email is mostly for information about courses. It's not an email to debate things. I'm old school. You have something to say, you put it on paper, you write it down, or you can type your letter, right? But you could still send it to me. And I promise to respond to, if you ask me something like that, that is so deep and meaningful, I will, of course, take time out of my schedule to actually provide you with a reply, with a written reply. By the way, in law, just so you all know this, and I hope you all know this, in law, you have to put everything in writing. So when you are expressing your beliefs and when you want to justify your beliefs, and you should put it in writing, because that way you can commit it to memory. And also that you leave. We're not going to be here forever. I'm not going to be here forever. We may have eternal life in heaven, but we don't have eternal life here on earth. And I just want to make sure that our thoughts in the defense of truth remain somehow written on paper, or written somewhere, saved somewhere, before certain people or certain powers try to destroy it. They don't want, when I say they, I mean the powers that be. They don't really like truth. They don't appreciate when the people who are making an effort to share truth with you all, they don't want that. And so they make it very hard for people today to be engaged. The last thing that they would want, and again, I'm saying they, specifically the powers that be, the last thing that they would want is to have an informed population, to have an informed citizenry. So I do what I can. I was going to make this, actually, I was going to upload this video earlier, probably like around 7 o'clock in the morning. But then I realized I had some corn flour left over, and I wanted to make myself some, I like making myself kind of like George Washington. He used to make himself some, well, he used to have some cakes, but I make myself some corn flour pancakes specifically. And I quite enjoy doing that. And of course, there's all a process in that. Nothing like a good breakfast on a classic hot iron skillet. Made in America, by the way. I don't have any of these foreign products in my house. But anyway, here goes the lesson. All right. Now, in the previous section, remember that in the previous video, we talked about this statement. We also talked about antecedent versus the antecedent and consequent, if you recall, right? So, to give an example, we said, if you look at the previous video, we talked about the definitions of what antecedent and consequent was. So you might want to look at that before, if you haven't watched that video, before you watch this one. I was thinking of an antecedent and consequent today because I was having a little conversation this morning as I was shopping for some flour. I needed extra flour, and there was a girl I knew, and we were talking a little bit about theology. And she kept saying that she was trying to I think the exact statement she used was something like, I can be a friend to all, she said, which of course is nonsense, right? You can't love God unless you hate the devil. And you can't love right unless you hate wrong. If we put it in mathematical terms, or antecedent and consequent, if you don't hate the devil, then you cannot love God. So here we have a condition: you don't hate the devil, and the consequent of that would be you cannot love God. But anyway, let's talk about what this means here. Let's talk about this equation here. We confronted in the previous video the disconcerting reality that the so-called sentence x squared minus 5x plus 6 equals 0 is nothing more than a drifter. It lacks meaning until you anchor it in the proper context. And variables refuse to behave if you do not give them a structure, much like unruly children. But thankfully, the tradition we have here of functional notation is going to save us from any kind of ambiguity. So a good way to name your this sentence would be to use functional notation, P of x. And this sentence would be true or false for specific values that we assign x. But let's not forget, if you write P of x, that does not make it a statement. It waits in limbo. It's because it's truth or falsehood. It's going to hang in the balance until x takes a specific value. So you have two examples here. When x equals 2, P of 2 is true. But if x equals 4, P of 4 is a false statement. Much like idle gossip, P of x is meaningless unless tethered to context. And as people who want to improve in our mathematical thinking, we graciously assume the default stage for such variables to be the set of real numbers, unless you are told otherwise, unless you're informed otherwise. So today we're going to introduce quantifiers. It's an antidote to vagueness. And I know there are some commenters who disagree with symbolic logic. It's an interesting discussion in either case. But for this series, I am assuming, I am taking as reality symbolic logic, because it is a fact that you have to learn it if you want to communicate to a broader range of mathematicians. But with their help, with the help of functional notation, we elevate P of x from a wandering phrase, and now it becomes a definitive statement. Notice what we have here. The quantifiers, we say that they are used to avoid ambiguity. That's why you got to know the symbols that I mentioned in the previous videos. I linked it below. The upside down A, I assume you're already familiar with that. And that is called the universal quantifier. It's read for every, for all, for each. And it steps in demanding that P of x holds true for all x in the real numbers. So we now have also an existential quantifier. It's a more humble and not as universal of a statement. It's a more truthful statement, though. There exists an x such that x squared minus 5x plus 6 equals 0. Indeed, that claim is true, because the roots of the equation, in case you have forgotten your algebra, are x equals 2 and x equals 3. And that's why we use, in mathematical shorthand, these, I put here some definitions. Make sure you know these symbols. The first E, the one that looks kind of in reverse, means it's called the existential quantifier. And the one that looks more scripted can be read as such that. So the first symbol, the one all the way on the left, it's really a delightfully concise way of avoiding. You don't want to get too verbose when you are trying to prove something. All right. Now we turn to a simpler declaration. Let's turn to a simpler declaration I'm going to share with you all. All right. What about this example here? We have a statement, and you should be familiar with the symbols used. We're saying there exists a number less than 5. So in the language of quantifiers, this becomes, we would write it in the way that you see on the board. And or if you're a minimalist, and we have some minimalists these days, minimalist purists perhaps, then you would want to have this one here that I'm circling in red. So here the understanding is that x represents a real number, and there's no need to state the obvious. Mathematics rewards brevity. I've often said that mathematicians, we are lazy, not in the negative sense of the word, but in a positive sense. If we can simplify something, we will. Now, what about the statement that you see next? If x is greater than 1, then x squared is greater than 1. Some may thoughtlessly scribble it down as it stands, but the discerning mathematician will recognize the tacit assumption of universality. And hence the proper way of writing this in symbolic logic would be like this. So this really underscores a vital principle. If a variable appears in the antecedent of an implication without explicit quantification, the universal quantifier is understood to apply. In other words, you leave no room for ambiguity, lest chaos reign in your proofs. But what about negation? Because we haven't really discussed, we have to see how the conditions that apply. So here's a statement. Everyone in this room is an illegal immigrant. What condition must apply to the people in the room in order for the statement to be as false as a socialist utopia? Do we need to sniff out every person in the room and prove that they are all legal citizens? Must everyone be a legal citizen? No. It is sufficient that at least one person be a legal citizen in order for the statement to be false. And one counterexample is all it takes to shatter the illusion of universality. If you want to write it symbolically, and I hope you've been studying the symbols, here is what it would look like. Take a look at this. And now you realize that this is an application of when we use and how we use the symbols. So the first one, if you look at it as a translation, it is not true that all people in this room are legal citizens. That's logically equivalent to saying there exists at least one person in this room who is not a legal citizen. Then you have another fun twist, sort of. There exists at least one legal citizen in the room. And what happens when we toss that statement into the negation blender? Well, you get this one. You get the second, this right here. And in plain English, if there isn't even one legal citizen in the room, then everyone must be an illegal immigrant. And you see how those universal and existential quantifiers dance around each other like old rivals at a duel? One takes the high road, the other takes the low road. Many people today take the low road, especially in America today in 2025. But they're always connected in some way. They drag down the rest, don't they? So the next thing we have to talk about is, all right, now what about the final part of this video? What about proofs? I sort of want to give you a gentle introduction to inductive versus deductive reasoning. Because in the first videos of this series, we began our journey through the hollowed halls of logic. I sort of gave you a foundation, an introductory foundation. Now, don't panic. We're not here to just toss around fancy terminology, though I'm sure the vocabulary is enough to send some people into a full-fledged existential crisis. No, our true mission is far grander. We have to read and write mathematics. But to accomplish this, you need more than a good dictionary. You need syntax. Yes, syntax. It is the very glue that binds statements together to form what is perhaps the most elusive and really the most intimidating creature in all of mathematics, the proof. But fear not, because we are going to ease into it like a seasoned surgeon handling a scalpel. First, if you take a look at the two main types of logical reasoning, you need some vocabulary here. You need to know the difference between inductive and deductive reasoning. And once we understand that, you can think of them as the sort of the bread and butter of mathematical thinking. And one of them can be a bit too soft and squishy. So perhaps so many people today would like it. But let's talk about a function here as an example. If we look at the function f of n equals n squared plus n plus 17, if we consider that. Now, if you're new to mathematics or just pretending to be, don't worry. I'll hold your hand through this one. When you plug in for this function various positive integers, you're going to start to notice something curious. First, I want you to try it. Pause the video and start plugging in numbers, positive integers, and let me know what output you get. Did you pause the video? Well, if you notice the output, you're always getting a prime number. By the way, if you don't know what a prime number is, it's a number greater than 1 that can only be divided by 1 and itself. It's exclusive, almost like the cool kids club of numbers, but in a good sense, not in the clownish sort of way. I mean, look at, if we plug in some numbers, we get very good results. Like if you do f of 1, if you evaluate it at 1, you get 19. If you evaluate it at 2, you'll get 23. If you evaluate it at 3, you'll get 29, etc. So in every single case, you're noticing something. It's almost like magic. Every number that comes out of this function looks like it could hold the keys to some kind of conclusion. Now, naturally, we have a human instinct to declare, I've discovered something profound. This function will always give us primes. And this is what we call inductive reasoning. It's like seeing a few red apples in a basket and concluding that the whole orchard is full of nothing but red apples. You've made a generalization based on specific observations. We do it all the time. Now, it's not always true in the real world, but it is a very important property of technique in mathematics. Now, I've often done that myself. I've looked at people who, the kind of people who are always drunk, always smoking weed, and there's a very common pattern in their lives. And it's often they don't end up very well, do they? A lot of people who do damaging things in the long run they don't end up doing very well in life. You see that all the time. But anyway, if we let P of n represent this sentence as this function as a prime number, you can ask the big question. Is it true? Is this true for all positive integers? Now hold on, let me stop you right there. No, we have not proved it's true. You see, while it's true that this function produces primes for many values of n, it has not been proven true for all values of n. And here's the thing, we cannot prove it for all n because it turns out that the statement is actually false. You cannot just blurt out a grand conclusion like that without some cold, hard evidence to back it up. And how do we know that this is false? The beauty of counterexamples. So what happens if n would equal 17? Then you would have the value, if you evaluate it at 17, you have 17 squared plus 17 plus 17. And now you have 17 times 19. And there you have it. It's really a counter example. It's really glorious. It's screaming at you, I'm not prime, and I won't be prime. There are other counter examples too that you can use. N equals 16 comes to mind. But you only need, as we said earlier, you only need one counter example to prove that this statement, as the statement we were saying, is false. Now let's pause for a moment, and we should reflect on this tale. Inductive reasoning has its place. Indeed, it is the very foundation of most scientific experimentation. But in the rigorous world of mathematics, we are not scientists. We are mathematicians. We go higher than that. The slightest slip could send you off the rails. It's not enough to make sweeping generalizations based on a few successful observations. You must have the proof to back it up, or else you're just chasing shadows. So in the example we just saw, you see why you cannot rely on inductive reasoning alone to build mathematical certainty. You don't have to despair, though. Inductive reasoning is useful, and it is often the spark that ignites the conjectures, which, once proven, become the theorems that guide our mathematical universe. But always remember, dear students, when you step into the world of proofs, the stakes are high, and only the sharpest logic will see you through. So we're going to look at more counterexamples to some statements. All right, so here are two statements that I want you to provide a counterexample for. The first one, all birds can fly, and the second statement, every continuous function is differentiable. Pause the video and let me know. Think about it, put it in your notes. All right, so here, if you thought about it, in the first case, any flightless bird can serve as a counterexample. You could use an ostrich. The second sentence, you can think of, you should know by now, the absolute value function. It is continuous for all real numbers, but it is not differentiable at the origin. So that's something to keep in mind. Secondly, we need to talk about a function. If we consider the function, let's say g we're assuming n and m, by the way, must be positive real numbers, positive integers, I should say, n squared plus n plus m. And if you think about the previous example, you saw that for the values of 16 and 17, you've got 17 squared as an answer, right? So if we start by plugging in some numbers here, take a look at what happens. If we have 1 and 2, the value of this statement is 4, which is also the same as saying 2 squared. If you use 2 and 3, the value becomes 9, which is the same thing as 3 squared. I want you to plug in some more numbers like 5 and 6 and see what happens when you do that. We're diving into the sea of logic with you should have the enthusiasm of a mathematician who knows the value of a good theorem. Now, we have some examples so far. We have 2 squared. We could use 1 and 2. If we use 2 and 3, you get 3 squared. We can now form a conjecture. What is the conjecture that you can come up with? Using inductive reasoning, by the way. Right? So if you have been practicing your symbolic logic, then you can figure out and Q of n is the statement that you could use So is this conjecture true? It turns out that it is. Unlike some politicians' promises, this one holds water. And how do we prove that? How do we prove that? We can now use the familiar laws of algebra. So, first of all, if we are going to prove this statement, we must have, this is by definition of g of n or n plus 1, you now have n squared. So let me see if I can make this neater. Now, this is by definition. Now, n plus n obviously is 2n. So you have n squared plus 2n plus 1. You can factor this neatly. And you can also simplify the writing of this. It's just really n plus 1 squared. The proof is complete. And this is deductive reasoning at its finest. You build it from logical steps and you power it by algebraic consistency. We didn't just stumble across an answer like some low-level guesswork. No. If you walk the straight and narrow path and fueled by the universal truths of maths, no shortcuts, no fluff, just pure logic here. And here is the cherry on top of this sort of impeccable proof.
If you have G of 124 and 125, let's say, you have 125 squared. You didn't even have to lift a pencil to compute it. And why is that? Because we apply the power of deductive reasoning. You take a general principle and apply it to a specific case. It's almost like a master chef knowing exactly how long to roast that turkey. There's no calculations here, just confidence. All right, now we have to talk about implications. In what way did we use deductive reasoning to prove what we just said? And the most common type of mathematical of mathematical theorem can be symbolized by P. Let's see if I can use that symbol again. And again, I told you to review those symbols. So definitely watch the previous videos. All right, now P and Q here are what we call compound statements. What we are saying essentially is that if P is true, then Q must follow. Sounds like a no-brainer, right? Well, to prove this, we have to show that whenever P is true, Q cannot be anything but true. If P is true and Q is false, we have a serious issue. Like showing up to a math class unprepared. It's not going to work well for you. And so to prove the implication, you need to have what we call, you need to build a logical bridge. And those are the building blocks of the proof. You need definitions, you need axioms, and you need previously proven theorems and logical implications that follow from earlier statements. And if you are the architect of this bridge, you need experience, intuition, perseverance, and just trudging along. If we want to assemble the bridge, you often have to start from both ends and work your way toward the middle. So picture it, on one side, you're asking, what do I need to prove Q? And then on the other side, you're starting with P and asking, what can I conclude from P that gets me to Q? And eventually the two sides meet. It's almost like a beautiful marriage of logical reasoning. And voila, your proof is complete. So let's have some examples that we can use. All right, so if we revisit the result, we're going to take a little stroll here to see how the process works. So P implies Q. We're going to see how mathematical theorems blossom and deductions weave like vines. So one way to frame what we were just discussing about building the actual bridge is we have hypothesis and we have conclusion. So we could call the hypothesis P and the conclusion Q. So the hypothesis will be and of course we have the conclusion, which we said was Q. Now, from here, we want to reach the grand finale. Q, we first have to figure out what leads to it. So enter stage left. We have Q sub 1, we can say, and Q sub 2. And if we use Now we're going to multiply out the product, because this simply states we have the definition here of a square. There's nothing flashy here. It's just a classic fact. So if we multiply these, you should know you should be getting n squared plus 2n plus 1. And voila, you have an expanded form here it's sparkling with clarity, and it matches the definition that we discussed. You see that there's an elegant chain in this discussion, right? What is the elegant chain here? This n squared plus 2n plus 1. Now, if you work backwards, because at this point, the trail goes cold. So we have to return to our hypothesis P, almost like detectives retracing steps. Now, P told us about G of n and n plus 1. So our first move is you have to plug in the definition of G, right? The definition of G, which we said was n squared plus n plus parentheses n plus 1. That's your aha moment. It flows beautifully into Q sub 2 because you're connecting the hypothesis to the conclusion in one smooth bridge. So in other words, P implies P sub 1. And what else can we say about that? It also, the P sub 1 implies Q sub 2, which implies Q sub 1. And from there, we have Q. So what we have here is a span of logic. It's built with algebraic precision, and it's reinforced by the unshakable laws of reasoning that God has given us. Now, there's also a bonus here. There's something called the contrapositive twist. In any implication, P implies Q, you have something of a shadowy twin, and it's called the contrapositive. Now, the contrapositive is often written with looks sort of like that, which means that not Q implies not P. And now don't be fooled. The logical sibling may seem different, but it's really a perfect clone in disguise. Now, to prove that P implies Q, you can always prove the contrapositive instead. You can use the truth table because truth tables don't lie, and they confirm the equivalence with precision. So the next time someone challenges your proof, just casually pivot to the contrapositive. It's like sort of showing the reverse angle in an instant replay. Math will always have your back. It is the language of God. I hope this video was useful to you all. And if it, just let me know in the comments if it was useful to you. And if it was, I ask you that you continue to subscribe to this channel. Let's get up to 10,000 subscribers. We can do this. Thank you all, and God bless.